On February 27th, 2026, a spacecraft 15 billion miles from Earth did something it does routinely, something it has done dozens of times over the last 5 decades without incident. It rolled. A slow, deliberate rotation, commanded from a control room in Southern California, designed to swing one of its instruments through a full circle so engineers could calibrate a magnetometer reading interstellar magnetic fields no human has ever touched. This maneuver had a name, a checklist, a predictable outcome. It was not supposed to be the moment everything nearly went dark. But when the data finally crawled back to Earth, more than a full day later, the engineers watching the numbers saw something they were not expecting. Power was dropping. Not gradually the way it always drops. 4 watts a year, a slow bleed the team has tracked for decades. This was sudden, sharp, enough that if it had continued even a little further, an automatic system buried deep in the spacecraft's 50-year-old architecture would have taken over control entirely, shutting down systems on its own with no way for anyone on Earth to intervene in real time. Engineers call it the undervoltage fault protection system. Think of it as a self-preservation reflex, hardwired into a machine that has been alone in the dark for longer than most of the people currently monitoring it have been alive. And on that day in February, humanity's most distant spacecraft came closer to triggering that reflex than it had in years. This is the story of what happened next, why a routine, in turn, nearly forced NASA's hand, and what Voyager 1 has been quietly telling scientists from beyond the edge of our solar system that nobody has been able to fully explain since 2017. Stay with me, because by the end of this, you'll understand why a machine running on less power than your porch light might be the most important thing humanity has ever built. I'm your host, and this is your channel. If stories like this are why you're here, subscribe now, because we're just getting started. To understand why a simple roll maneuver could push a spacecraft to the brink, you have to understand what Voyager 1 actually is right now, in 2026, and how little room for error it has left. It launched on September 5th, 1977, on a mission built to last 5 years. Fly past Jupiter, fly past Saturn, send back some photographs, go quiet. That was the plan. Instead, it kept going, using the gravity of each planet like a slingshot to add speed and reach. And on August 25th, 2012, it crossed the heliopause, the boundary where the sun's influence finally gives way to the space between stars. It became the first human-made object in history to leave the solar system entirely. It is still out there, still transmitting, still, as of this year, sending back real scientific data from a region of space that no other instrument humanity has ever built, has ever physically touched. But everything about keeping it alive has become an exercise in trading away pieces of itself, one at a time, to buy a little more time. Voyager 1 doesn't run on batteries or solar panels. Out where it is now, more than 15 billion miles from the sun, sunlight is far too weak to power anything. Instead, it runs on 3 radioisotope thermoelectric generators, containers of decaying plutonium-238 that convert heat into electricity as the radioactive material slowly breaks down. At launch, those generators produced about 470 watts. Today, after nearly 49 years of continuous decay, they produce less than half that, and the number falls by roughly 4 watts every single year. A slow, unstoppable countdown written into the physics of radioactive decay itself. There is no way to refuel it. There is no way to send a technician. Every watt that disappears is gone permanently. And the team at NASA's Jet Propulsion Laboratory has spent years making increasingly difficult decisions about which systems get to keep, drawing power and which ones have to go dark forever. Of the 10 original scientific instruments Voyager 1 carried at launch, 7 have already been shut down, not because they broke, but because there was no longer enough electricity to run them. That is the context you need to understand what happened on February 27th. The team had scheduled a routine roll, the kind of maneuver Voyager 1 has performed without drama for decades, this time to calibrate its magnetometer, one of only 2 scientific instruments still functioning on the entire spacecraft. But when the telemetry came back, more than 23 hours after the maneuver, because that is how long a signal now takes to cross the gulf between Voyager 1 and Earth, the engineers saw a power drop they had not planned for and could not immediately explain. Kareem Badruddin, the Voyager mission manager at JPL, later compared the spacecraft's fault protection system to a safety net under a trapeze artist. It's there, he said, but the trapeze artist should never actually need to fall into it. Getting caught by that net doesn't just mean surviving. It means a long, complicated, uncertain recovery process, sending new commands across billions of miles, waiting nearly 2 full days for each round of confirmation, hoping nothing else goes wrong while the spacecraft is essentially running on autopilot in survival mode. The team decided they would rather make the hard call themselves than let the spacecraft make it for them. So on April 17th, 2026, they sent the command to permanently shut down the low energy charged particles experiment, an instrument that had been measuring ions, electrons, and cosmic rays streaming in from both our solar system and the wider galaxy since the year the spacecraft launched. Nearly 49 years of continuous operation ended in a single afternoon to buy the rest of the spacecraft a little more breathing room. Losing that instrument was not a small thing. The Low Energy Charged Particles Experiment, LECP for short, was one of the primary tools that told scientists exactly when Voyager 1 crossed out of the solar system's influence and into true interstellar space back in 2012. It has spent over a decade since then quietly mapping the pressure fronts and shifting particle densities of the region beyond the heliopause, a place where the only 2 functioning instruments left, out of 10 spacecraft on 2 probes originally launched with a full suite each, are now a plasma wave detector and a magnetometer. Voyager 1 is down to 2 working senses out of what was once a much richer set, and every one of those remaining senses is being kept alive on a power budget smaller than what it takes to run a couple of LED light bulbs. But here's the part of the story that almost nobody outside the mission team has been talking about, and it's the reason NASA didn't just accept this as a quiet, final loss, because the same power crisis that forced the LECP shutdown had already put something else in motion. Engineers at JPL have been developing an experimental procedure, one they've informally nicknamed the Big Bang, that restructures how electricity flows through the spacecraft's remaining systems, attempting to squeeze out extra capacity from components that are currently running less efficiently than they could be. It is delicate, genuinely risky. Work on a machine with no manual override, sitting so far away that a single miscalculated command could end the mission instantly with no chance to correct course. So the team is testing it first on Voyager 1's twin, Voyager 2, which has slightly more spare power and is somewhat closer to Earth, making a potential failure less catastrophic if something goes wrong. Those tests were scheduled for May and June of this year. And if they succeeded, the plan was to attempt the same procedure on Voyager 1 no earlier than July 2026, which means right now, as you're watching this, that attempt is either already underway or about to begin. And here's the detail that makes it worth paying attention to. If the Big Bang procedure works on Voyager 1, there's a real chance the LECP instrument that was just shut down in April could be switched back on. Matt Hill, the instrument's principal investigator at Johns Hopkins, said the team is holding out hope that whatever surprises are still waiting in that distant region of space won't stay hidden for good. Nobody is promising it will work, but nobody at JPL has given up on it either, because with this mission, the history of assuming something was finished before it actually was has a track record of being wrong. Now, here's why all of this matters beyond the mechanics of watts and instruments and fault protection systems, because even while Voyager 1 has been losing pieces of itself one by one, the instruments still running have been sending back something that scientists have not been able to fully explain since they first noticed it. Starting in 2017, 5 years after Voyager 1 crossed into interstellar space, its plasma wave instrument began picking up a strange, continuous signal. Not the dramatic bursts scientists had already documented before that point, the kind triggered when a shock wave from a solar eruption on our own sun eventually rippled outward and slammed into the interstellar medium many months later. This was different. A faint, narrow, persistent hum sitting quietly in the data in between those known bursts, showing up again and again, year after year, in a way no existing model had predicted should be there. Cornell astronomer Stella Koch-Ocker, who led the team that first identified it, described interstellar space before this discovery as something scientists imagined would behave like a quiet, gentle rain, an even low-level background with occasional bursts, like distant lightning in a thunderstorm. What Voyager 1 found instead was that the quiet moments between the bursts were not actually quiet at all. There was a constant low murmur running underneath everything, a signature nobody had built into their models because nobody had ever had an instrument sitting inside interstellar space long enough, continuously enough, to notice it. Published in Nature Astronomy, the research built on this signal gave scientists something they had never had before, a continuous, steadily sampled measurement of interstellar plasma density, rather than the scattered, isolated snapshots. Earlier instruments could only capture during rare solar-triggered events. It let researchers trace fluctuations in that density across distances measured in fractions of an astronomical unit, revealing turbulence and structure in the space between stars at a level of detail nobody expected to find. But the researchers who published this finding were careful to say something else too, something that has quietly remained unresolved in the years since. They do not yet know exactly what is causing the hum. There are 2 leading explanations, and distinguishing between them requires more data than Voyager 1 alone may ever be able to provide. The first possibility is that the signal comes from thermally excited plasma oscillations, the natural vibration of charged particles interacting with their surroundings, a phenomenon that fits inside existing physical frameworks without forcing anyone to rewrite them. The second possibility is something called quasi-thermal noise, a related but meaningfully different physical mechanism, one that would require scientists to reconsider some of their existing assumptions about how the interstellar medium behaves. Both are legitimate, both are backed by real physics, and researchers have openly said that only new data, either from Voyager itself or from a future mission built specifically to study interstellar space, will be able to settle the question. As of today, no such mission exists, none is funded, and if one were greenlit and launched right now, it would take at least 2.5 decades to reach the same boundary Voyager 1 crossed back in 2012. Which brings us to the timeline that makes all of this feel less like a leisurely scientific mystery and more like a closing window. Voyager 1's power is not going to stop declining. Every year, roughly 4 more watts disappear. And every year, the team has to make harder decisions about what stays on and what goes dark permanently. Because there is no way to reverse a shutdown once it happens, unless something like the Big Bang procedure changes that equation. NASA's own engineering projections put the point where the spacecraft's remaining instruments finally lose enough power to function sometime in the early 2030s. After that, Voyager 1 will still exist. It will still be moving, roughly 38,000 miles an hour deeper into interstellar space every single hour that passes. But it will be silent. No more data, no more hum. No more chance to answer the question about what exactly is producing that persistent plasma signature, at least not from this spacecraft, and at least not for a generation, until some future mission might eventually reach the same boundary and pick up where Voyager 1 left off. And before that silence arrives, there's one more milestone already locked into the calendar, one that has nothing to do with instruments or power budgets and everything to do with pure distance. On November 18th, 2026, at 2:16 and 12 seconds in the morning, Pacific time, Voyager 1 will become the first human-made object in history to reach a distance of exactly 1 light day from Earth, more than 16 billion miles away. At that distance, a radio signal traveling at the fastest speed anything in the universe can travel will take a full 24 hours just to arrive. Send a command on a Monday morning, and you won't know if it was received until Tuesday morning, and you won't hear back until Wednesday. Every single exchange with this spacecraft, every diagnostic check, every attempt to nurse a few more years of life out of a machine built during the Ford administration, now has to be planned around a 2-day round trip of nothing but silence and waiting. No human-made object has ever operated at that distance before, and Voyager 1 will cross that threshold this year while it is still alive, still transmitting, still telling us things we don't fully understand yet. So here is where this actually leaves us. A spacecraft that nearly tripped its own emergency shutdown system during a routine calibration roll in February. A team of engineers who chose to sacrifice one of its last remaining senses in April rather than risk losing everything to an automated failsafe. An experimental power-saving procedure, tested first on its twin and now, this month, potentially being attempted on Voyager 1 itself, that could either buy years of additional life or risk ending the mission outright if something goes wrong at 15 billion miles with no way to intervene directly. And underneath all of that, a persistent, unexplained signal that has been humming quietly in the data since 2017, one that 2 competing physical explanations still can't fully account for, with no new mission on the books to help settle the question anytime soon. This is not a spacecraft quietly winding down into retirement. It is a machine running on a fraction of the power it takes to light a room, threading a needle between survival and shutdown, still reaching back across an ever-growing gulf of silence to tell us something true about a part of the universe we have never been able to observe from anywhere else. The signal is still coming. Nobody knows exactly how much longer it will last. And right now, in a control room in Southern California, a team of engineers is watching a procedure unfold on a spacecraft they built before most of them were born, hoping it survives long enough to keep talking. If this kind of story is what you come here for, hit subscribe and turn on notifications, because we're going deeper into the edges of what we actually know next time. Drop a comment telling me what part of this stood out to you most, and share this with someone who needs a reminder that some of the biggest mysteries in science are unfolding right now, quietly, 15 billion miles from home.